Okay, we're very happy to have Erez Shochat here to give the second part of the talk that Ermek started last week on the automorphism groups of countable short recursively saturated models of PA, and particularly on invariant cuts. So go ahead, Erez.
Well, thank you, Atar, for having me, and thank you for the MOPA organizers. As Atar mentioned, I'm going to continue the talk of Ermek Nukaidarov from Penn State University on the automorphism groups of countable short recursively saturated models of Peano arithmetic. Just for completion, I prepared some background stuff, so I'll start with that. Um, so just a few definitions of recursive saturation and bounded recursive saturation. A model is recursively saturated if it realizes every finitely realizable recursive type with a finite number of parameters. So I assume the audience here knows this definition and familiar with recursively saturated models. So I'll move on. A type P of VA is bounded if it contains the formula V is less than T of A for some Skolem term. So if a type contains, for example, V is less than A cubed, then it is bounded. And then a model is boundedly recursively saturated if it realizes every finitely realizable bounded recursive type with a finite number of parameters. So just one condition we added was that the type has to be bounded. Um, Initially, in papers from the 80s, these models were called short recursively saturated. So so we reserved the word short for a specific case of boundedly recursively saturated. Now, um, every recursively saturated model clearly is boundedly recursively saturated. Um, and every cut, every elementary cut of a recursively saturated model is boundedly recursively saturated. So every recursively saturated model, as I said, is boundedly recursively saturated. Every elementary cut of a recursively saturated model is boundedly recursively saturated. Now, some of the cuts of of recursively saturated models are recursively saturated, but there are countably many cases when they are not recursively saturated, but just boundedly recursively saturated. And those will be the short models, by the way, the short recursively saturated models. A few important facts about countable recursively saturated models, which are probably known to most of the people in this talk, but I just wanted to mention them. Of course, from Gödel, it follows that there are continuum many theories extending Peano arithmetic, and combining this with the result of Barweis and Schliff and Reser, which says that every consistent theory in a finite language has a countable recursively saturated model, it follows that um, there are continuing many countable recursively saturated models of Peano arithmetic. For each such theory extending PA, there is at least one, but actually there's much more. Each one of these theories actually has, based on the standard systems, which there are continuum many standard system for each theory, um, or models with there are continuum many models with different standard system for each theory. Each one of these theories has actually continuum many countable recursively saturated models which are pairwise non-isomorphic. If you have a different standard system, the models are not isomorphic. If you have a different theory, the models are not isomorphic. So you have continuum time continuum, still continuum, but that's so we have a lot, but actually this is the most we can get. Um, it is well known that two countable recursively saturated models of Peano arithmetic, M and N, are isomorphic if and only if they have the same theory and the same standard system. So as long as they have the same theory and the same standard system, they will be isomorphic if they are countable recursively saturated. Any questions about this so far?
Uh, y- yeah, can
Yes.
I ask you? This is somewhat basic. So I guess the idea is um, every Scott set, every Scott set essentially corresponds to a recursively saturated model. Is that the idea? Or every Scott set that codes its theory corresponds to wait, so if you have a theory T and a Scott set that T is an X, then there's a recursively saturated model, a countable recursively saturated model with that standard system.
So for every Scott set, I believe there will be a model. I have to check the
I mean, it's
details.
countable, a countable
But
Scott set, right?
right, right,
So
right.
yeah,
So every countable Scott set,
okay.
there will
That's,
be a model. I'm not sure if there will be a model containing that Scott set or exactly with the same with that Scott set,
okay.
but there will be a model containing
I believe
that Scott
statement.
set, and you can extend it. You can keep finding like using binary argument,
Mm,
add coded sets and find continuum many
X,
different
okay,
Scott sets by extending it.
right.
Ermek, you wanted to mention something?
I believe some statement might go something like if T is like theory and X is a spot set, if T belongs to
Yeah,
spot set X, then there is countably recursively saturated
yeah,
model.
yeah.
Yeah, blah,
That's
blah.
what I was
Yeah.
trying to
Right.
ask.
Yeah.
Okay,
Okay.
and so then there'd be continuing many of those because you can
Yes.
start with T and then
Correct.
kind of build it above that.
Yeah. Yeah.
Okay, okay,
And that's for every theory. You
yeah,
can do that. So continuum times continuum, but again, using back and forth argument, you can show that uh, two such models that are recursively saturated and have the same theory and same standard system must be isomorphic or are isomorphic. Okay. So let's move on now to talk about short recursively saturated models. Let M be a model and uh, uh, not end. Let M be a model of PA and A an element of M. Let MA be the smallest elementary initial segment of M containing A. So here's the picture. You have a model M and you have A in M. We look at MA, we define it to be the smallest elementary initial segment or small elements and elementary cut of M containing A. Models like this are called short models. One reason for that is that MA can be shown to be all the x's such that with that are less than or equal to some Skolem term of A. So everything that's less than A is going to be there. Everything that's less than A squared will be there. Less than A cubed will be there. Less than A to the A many times, etc., etc. Everything that can be defined from A and everything less than that is going to be in that model. So those are called short models versus tall models that don't have an element that's cofinal, can be define stuff cofinal in them. So, as I mentioned, if M is recursively saturated, MA any cut is boundly recursively saturated, in particular MA, but it's actually proper elementary initial segment of M because M, a recursively saturated model, is always tall. You can define a type X greater than T of A for every T, and that will be somewhere above this, and you can do it for every A in the model. So there's no element in the model that defines cofinal set in the model for recursively saturated. So recursively saturated are tall. A short recursively saturated with the newer definition they'll be strictly short. They'll be boundly recursively saturated, which are short. So models which are boundly recursively saturated and are short are called short recursively saturated. And every countable short recursively saturated model has a proper elementary end extension which is recursively saturated. I'm not sure who proved it first, maybe Roman Kozak, my advisor. So every countable short recursively saturated has an elementary extension which is recursively saturated, which implies, I think he proved it for every model, not just for countable. I think countable might have been Smorinsky's result. So if you start with any short recursively saturated model, you can show that it has an elementary n extension which is recursively saturated. So you can think of any short recursively saturated model as living inside a recursively saturated model in this way. So this picture is always the case. So we can always draw this picture when we think of short recursively saturated models. Okay, when we study short recursively saturated model, the stuff that's very close to MA, to the end, to A, is very important. And it has a name, it's called the gap. So let's talk a little bit about gaps. If M is a model of Peano arithmetic and A is an element in M, then the gap of A is all the elements that are close enough to A. So it's all the B's, such that B, there's some terms, column term T, such that T of A is greater than B. Again, it could be the 8th prime after A. So it's something we can define if there's a term that's bigger than B, definable from A, then B is in end, B is greater than A, or if B is less than A, some B1 and B2 maybe. And there's a term such that T of B2 is greater than A. So all the stuff that's a little above A and a little below A, not a little, it's infinitely big, but the stuff that we can define something above A and from stuff below A, we can define elements. This is called the gap of A. And it can be shown that the set of gaps forms a partition. So if B is in the gap of A, the gap of B equals the gap of A. And then there is a partition of gaps looking like this. And it's actually dense linear order. So this is in the next slide. The gaps of a countable recursively saturated model form a countable partition. It's always a partition, even if it's not a recursively saturated model. But in particular, the countable recursively saturated form a countable partition of the model, and the ordering of the set of gaps is a dense linear ordering with the first element, gap of 0. So if 0 defines non-standard elements, if it's not a model of true arithmetic, we can define non-standard elements. This will be the gap of 0. That will be the first gap, and then M has no last gap. So that's how the picture looks like. An important fact that I didn't write, so I'm going to mention it now. Automorphisms of models of arithmetic sends gaps to gaps. So gap of A could move to gap of B, but the entire gap is going to move to the entire gap. It's not going to move half and then half to a different place. For countable short recursively saturated models, if the model is extremely short, so if we call this M of 0, this is all the elements up to gap of 0, but gap of 0 will be everything from 0 to the end here. So if the model is like this, it's still short recursively saturated M of 0. We call this the extremely short model. There's only one gap in that case. Otherwise, if A is greater than the gap, bigger than the gap of 0, like in this picture, the ordering of the set of gaps of MA is a dense linear order with the first element, again, gap of 0 will be the first element, gap of A. So if we're talking about short recursively saturated, there'll be a last gap. And it's the gap defined by the gap of an element that's cofinal or defines a cofinal set in A. So we have a last element, first element, and everything here will be dense linear order, countable dense linear order. Okay. Any questions about this? not, let's move on. So we are still doing well in time. Short countable recursively saturated models. Let's look at some facts. We talked about the facts with countable recursively saturated. Let's add a few more. So remember, just quickly, we have continuum many theories extending PA. Each one of them has a countable short recursively saturated model. And each one of these, you can show that there are continuum many standard systems that have this theory, and therefore there will be continuum many countable short recursively saturated models which are pairwise isomorphic. Remember, that was all for recursively saturated models. That's the most you could get. But now that we have a last gap, it turns out that if elements are realizing different types in the last gap, let's call this MA and MB, even if it's the same model M, but we just cut it at A and this one we cut at B, if those don't realize, if the last gap has no elements realizing the same type, those will be non-isomorphic because the last gap has to be mapped to the last gap. But remember from that if there's an automorphism moving an element to another element, they must have the same type. But if the types in this gap are different than the type in this gap, you cannot have an isomorphism between these two models because this last gap has to be mapped into this last gap, but don't have the same types. So each one of the recursively saturated models has countably many short recursively saturated elementary initial segments, which are pairwise non-isomorphic, again, because they will realize different types. And it's proven based on work of Geifman already that even with minimal types, you can have countably many gaps that don't have the same types in them. So not only we have continuum times continuum, but now times aleph not many. Still continuum, but many cases. Smorinsky proved in 81. He actually proved the other result also, but I think it was known before. In the same paper, he proved the result for the recursively saturated. Two countable short recursively saturated models of PA, MA and NB, are isomorphic if and only if they have the same theory, the same standard system, and there's an element in the last gap of MA and an element in the last gap of NB such that they realize the same type. So as long as you can find one element in the gap of one model and one element in the gap of the other model that realize the same type, and if they have the same theory and the same standard system, there is an isomorphism between them. In particular, there's an isomorphism sending C to D. And again, you can do it by a back and forth argument. So this was proved in the paper by Smorinsky, which is the biggest treatment of short recursively saturated models in the 80s. It was specifically on these types of models, the paper. Okay, so these are the facts about short countable recursively saturated models. Really should have said countable short recursively saturated models. And let's discuss briefly arithmetic saturation because this is a very important topic. And we'll have a lot of distinction between arithmetically saturated models and models which are not arithmetically saturated. A model M is arithmetically saturated if it realizes every finitely realizable type, P of VA, which is arithmetic, not just recursive, but arithmetic, and not just in the model or in the theory, but in the type of B for some B in the model M. So it does realize like it has a stronger saturation. Every arithmetically saturated model, of course, is recursively saturated, but it realizes even more types. Interesting fact is that you can extend the standard system. You were mentioning standard systems. You can extend the standard system of an arithmetically saturated model to become a standard system or a Scott set of a model which is just recursively saturated and not arithmetically saturated. And you can keep going like that, changing it from a model which is arithmetically saturated to a model which is a standard system of a model which is not, and vice versa. Laurie Kirby, which is also on this talk, proved a lot of facts about arithmetically saturated models. I'm not going to use them now, so I'm not going to mention them. They're in part 1 of the talk. You can look at those results as well. Clearly, every arithmetically saturated model is recursively saturated, as I mentioned. Recursively saturated models which are not arithmetically saturated, we'll call them, or are called, just recently we started calling them this way. Erez started with this name, I think through the MOPA seminar, someone gave him this idea. So recursively saturated models which are not arithmetically saturated models will be called just recursively saturated. So when we study recursively saturated models, we can look at arithmetically saturated versus just recursively saturated and see if there are any differences. And it turns out there are a lot of differences. Similarly, you can show that if you have a bounded type, but everything else is the same in terms of realizing all these types that are arithmetic, just bounded. We'll call those, if they are short, also if the model is short, we'll call it short arithmetically saturated. In particular, if M is arithmetically saturated and A is any element in M, MA is going to be short arithmetically saturated. So it's going to realize it's going to be a short model which realizes every bounded type like this. And similarly, if we take a just recursively saturated model and we take an A in that model, they will have the same standard system. So it will still be just short recursively saturated. So it will realize again all bounded types that are recursive, but it won't be arithmetic. Okay, so that's for these terms. I'm going to use them later. And now we're ready to talk about the main part of this talk, and that's we'll focus on the automorphism group. Just going back for a minute. Again, once we had this characterization was also for recursively saturated, the next natural question was, okay, what about models that are not isomorphic? How different they are? What do they have in them that's different? And the natural question was to look at the automorphism groups of these models and see, can we find differences in the automorphism group? Since we know they're not isomorphic, something is different between them. Or do they still have the same automorphism group, or are their automorphism groups isomorphic or not? So it turns out that this was a very important question, and in the 90s especially, but even in the 80s.
Can I ask a question here before you move on?
Yes. Yeah, go
So
ahead.
this is about the Smerinsky result.
Yes.
If you have that they have the same theory and the same standard system, and they're short recursively saturated models, then they're both cuts of essentially the same recursively saturated model, yes? And so they might not be isomorphic, but would you be able to show that one is isomorphic to a cut of the other or something along those lines?
So you're asking about
The Smerinsky result.
with a model like this, with A and B, and maybe MA and M.
Well, I mean, just a priori,
Okay.
we don't know that, but because they
Right.
have the same theory and the same standard system, then
Correct.
there should be some M
Yes,
where that will
correct.
work.
Correct. You can map them to the same recursively saturated model, like and make an isomorphism to an initial segment of that model.
And
Correct.
so one of them is isomorphic to the cut of to a cut of the other. One of these M of A
Correct.
or N of B. Okay.
Yes, correct. That's always the case. Good observation.
Okay.
So yeah, one is always going to be isomorphic to a cut of the other. But if they have this same type in the last gap,
Mm-hmm.
they will be isomorphic to each other. Yes. But the interesting question is, okay, what happens with the isomorphism group and with the automorphism groups? And it turns out that there are a lot of differences, especially in the recursively saturated case. We already have a lot of proofs, and hopefully we can get more improvements in the short recursively saturated model. For a model of Peano arithmetic, we define a topology on the automorphism group of M by taking the basic open subgroups to be the stabilizers of elements. That is, all the subgroups of the form G of B, such as all the G's, all the automorphisms, such as G of B equals B. So all the so every subgroup of this form is a basic open subgroup. Okay, and from that you can build a whole topology. So again, I won't have time to go over all many details, many facts. I'm just going to skip to the main facts. Lascari 94, a very important result, proved that the automorphism group of countable arithmetically saturated models have the small index property. So every automorphism group of a countable arithmetically saturated model has the small index property, which means that the subgroup is open if and only if every subgroup is open if and only if it has a countable index. Now, whether a subgroup has a countable index, that's an abstract an algebraic property versus open subgroup, which is a topological group property, but we can retrieve the topology from using the small index property. So we can look at the subgroup and see if it has a small index, it must be open. And then we can talk about other subgroup, closed subgroup, based on whether we know already that some subgroups are open and which are open and which are not. So this is an extremely important result, because now every time we can prove something about if two automorphism groups are not isomorphic as topological groups, the small index property already implies that they must be not isomorphic as abstract groups. So even more a bigger difference in terms of those structures. The open questions that came up after this result were, do the automorphism groups of just recursively saturated has the small index property? Do those of short arithmetically saturated and just short arithmetically saturated have the small index property? So I believe that especially the first question about just recursively saturated was attempted, but unsuccessfully. And so far, there's no proof of that. And then when I was working on my dissertation, I was trying to look into that, but it turns out not to be a simple question. And so far, we don't have a result like that. That would help in our studies and in our research if we could figure this out. Okay, so I mentioned the big question, finding non-isomorphic automorphism groups of models which are not isomorphic. And already in 91, K. Kozak and Kotlarski showed that if M is a countable arithmetically saturated model and N is just recursively saturated, then I believe looking at maximal groups, they were able to show that the automorphism of M is not isomorphic to the automorphism of N. And together with Lascar's small index property, so they showed it as topological groups, but together with Lascar, this shows that it's actually not isomorphic as abstract groups. I used a similar argument in 2010 to show that if M is countable short arithmetically saturated model of PA, countable, yeah, and N is just short countable recursively saturated model of PA, then the automorphism of groups of M and N are not isomorphic as topological groups. I don't have the small index property to just say as abstract groups. So this is one difference, okay? So countable arithmetically saturated and just recursively saturated are not isomorphic, and in particular also for short, but as topological groups. So that's already two types of, or two classes of models that are not isomorphic. Another very important result from 1995 of Kozak and Shmerel is that if M and N are countable arithmetically saturated models and they have different standard system, then their automorphism groups are non-isomorphic. And this is huge because that gives us continuing many different types, because we have continuing many different standard systems for arithmetically saturated models. So now we have continuing many non-isomorphic models who are have non-isomorphic automorphism groups. Ermek Nokadarov discussed in the last in the first part of the talk the sketch of the proof of how to show the following result, which is an improvement to what we know. We didn't know much about this for short, but we couldn't get the whole strength of this result for that we have for arithmetically saturated. What Ermek showed was that if M1 and M2 are countable short arithmetically saturated models of Peano arithmetic, such that omega with the set of all set represented in the theory of M1, if that's a model of Ramsey theory on two on pairs with two coloring, then if the automorphism group of M1 and M2 are topologically isomorphic, then they must have the same standard system, which implies that if you have at least one of the models, and that would also follow from the next result, but if one of these models is a model of RT2, and you have M1 and M2 which have different standard systems, then they will have different automorphism, non-isomorphic automorphism groups. So again, we didn't know much about this, but he was able to show this, and hopefully will be published in our joint paper, which is now in the draft stages. But so that's looking at the standard system. So before we just looked at the difference between, which is also the standard system case, but we looked at the difference between just short recursively saturated versus short arithmetically saturated. The second slide was looking at the standard systems. And finally, we can look at the theory. Actually, we have one more thing to look at for short recursively saturated models. But looking at the theories, Kay showed that the automorphism group of countable recursively saturated models, true arithmetic, and true arithmetic is the theory of N, and models, the uncountably many other models of PA which are other than true arithmetic. Sometimes we just denote it as false arithmetic. Those are not isomorphic as topological groups based on looking at the normal subgroups, which I'll mention later. But he showed this, so he showed already theories that have different automorphism groups. And then Ermek Nukaidarov, who is writing the paper with me, proved in 2006 that there are additional arithmetically saturated models with different theories and with non-isomorphic automorphism groups. So he extended that looking at Ramsey theory, actually, similar ideas. And then Shmerel used his ideas and extended Ermek's results to infinitely many theories. So by now we know that there are infinitely many theories, but we don't know if it's for every theory versus standard systems for arithmetically, which we know that whenever they're different, they'll have different automorphism groups. Here, we don't have the full strength. We don't know if always when theories are different, we have different automorphism groups, but we know that there are at least infinitely many of those. So again, Ermek, one of his other results in the paper is that short arithmetically saturated models, and he discussed it again last week in the first part of the talk, that if M1 and M2 are countable short arithmetically saturated models, and if the automorphism groups are topologically isomorphic, then for every n, omega and the represented theory of with the represented theory of M1, if that's a model of RT2N, so now we can do pairs or triples or whatever other calling, but two colors, this will be a model of RT2N for every n, if and only if omega represented theory of M2 is a model of RT2N, and that implies models that have different theories if they have this condition, and they have different if they're not, one of them satisfies and one doesn't satisfy for a certain n, then they will have different not isomorphic automorphism group as a topological groups. Okay, so any questions so far? So I don't know all the details of his proofs because it was mainly his work. I'm gonna now move on to the next type of difference. So the first difference was looking at just recursively saturated versus arithmetically saturated. Second one was looking at standard system, and the third one was looking at theories. And finally, we're going to look at gaps, the last gap. So the next result, well, first I'm going to remind you a definition. And there were two different definitions of invariant, but they were turned to be equivalent for recursively saturated, but not for short recursively saturated. So I'll mention the one that's equivalent. That we need for short recursively saturated, and that's, I believe, this historically, in general, saying invariant means it's fixed. So we say that a cut I of M is invariant if it is fixed setwise by all automorphisms, i.e. G of I equals I for all automorphism G in G. So just a simple example, G of M0 must be M0. So M0 is invariant. So remember what's M0. We have N. M0 is the extremely short model, or the cut of where column closure of 0 is cofinal in that cut. So again, every definable element must be fixed by all automorphisms. Therefore, the supremum of that will be also fixed by all automorphism, but fixed set-wise, because there are still, especially in recursively saturated models, there are infinitely many, of course, non-definable elements that, and many of them realize the same type, and they are, you have continuum automorphism moving those elements there. So M0 is not fixed pointwise by all automorphisms, but it's fixed set-wise by all automorphisms. Nevertheless, Ermek mentioned that if you look at all automorphism which fix this M0 pointwise, so they fix the whole initial segment here, this is for all x in M0. So the automorphisms fix the whole initial segment. This is a normal subgroup because M of 0 is invariant. But it turns out there are, if M0 is not equal to N, there are continuum many invariant initial segments here for every recursively saturated model. But in short recursively saturated models, we actually get additional invariant initial segments, like M bracket A, which is the MA minus the gap of A. So it's this cut. That's the largest initial segment, elementary initial segment not containing A. That will be fixed as well. Okay, so let's move on. So again, as I mentioned, Kate proved that the closed normal subgroups of the automorphism group of a countable recursively saturated model of PA are exactly the pointwise stabilizers of the invariant of invariant initial segments. Again, we have the word closed, so if we prove something, we have to be careful if it's for as topological groups or not. I was in my dissertation, I was able to show similar arguments of actually arguments of Schmerl, who did a shorter proof of this result. I was able to mimic a lot of the arguments and show that the closed normal subgroups of the automorphism group of a countable short recursively saturated model of PA are exactly the pointwise stabilizers of the invariant initial segments. Using that, I used an idea that was given to me by my advisor, Roman Kozak, to show that there are two different possibilities. There's more than two, but at least at the last gap. If elements realize rare types, they will have continuing many invariant initial segments in the last gap versus models that don't realize rare types and will have no invariant initial segments in the last gap. Remember the closed normal subgroups correspond, it's called a Galois correspondence, they correspond to the pointwise stabilizers of invariant initial segments. So where did I get this picture from? Well, a type is called rare if it's the only element. If A, whenever A satisfies P, the type P, then for any other B in the gap, no other B realizes the same type as A. So A is the only element in the type realizing this type. But remember, types have to be mapped to the same elements of the same type, and the last gap of MA must be mapped to the last gap of another element if they're isomorphic, and an automorphism will map the last gap of MA to the last gap of MA. So A will have to go to A. So A is not moved by any automorphism, which means that the whole segments from 0 to A, or from the cut closed under exponentiation containing A, will be invariant. But if that's invariant, this means that this is a closed the stabilizers of this set make a closed normal subgroup. But again, if you have A is invariant, then anything defined from A is invariant, and limits of stuff that define from A, of cuts definable from A, are also invariant. So we get here now continue many invariant initial segments for rare types. On the other hand, if you have no rare types, you can show that there are elements that realize the same type of A very high in the model and very low in the model. There's no invariant initial segments at all in this model. The last non-trivial invariant initial segment is M bracket A. These gaps, by the way, that have rare types are called labeled gaps. Gaps that don't have any rare, realize any rare types are called non-labeled. You can think of the A as like the label of the gap. Although it's not unique, A plus 1 is also rare. You can prove. So we have these two pictures which imply the following. If the gap of A has elements realizing rare types and the gap of B does not have elements realizing rare types, then their automorphism group is not isomorphic, because this model excuse me, has no last. There's always a bigger one. There's no last invariant initial segment, which means there's no smallest non-trivial closed normal subgroup, versus this one that has a last invariant non-trivial initial segments, and bracket A, which implies a smallest non-trivial closed normal subgroup. So the isomorphism group of this model and the isomorphism group of this model, I should have denoted maybe by B, but think of these as different models, will be non-isomorphic as topological groups. So that was known already after my dissertation in 2006. And this is a new work that I started thinking about it during my dissertation, but didn't have time and then put it away. And now finally I looked at it together with Ermek. And I know I don't have much time, but I'll try to summarize it. So an important type of element is, or type of a type is selective type. A type is selective if whenever A is in M satisfies a model P, a type P, for any B, for any B in column closure of A, not column closure of 0. So every B that's definable from A must be definable from B. If B is in the column closure of A minus column closure of 0, so it's non-definable element, then A must be in the column closure of B. There's equivalent definitions, but I don't have time to talk much about them. So here's A. Here's column closure of 0, defines elements here. A, besides column closure of A, contains column closure of 0, but it contains also other elements like A plus 1, etc., etc. So if you have a B definable from A, like T of A is B, there will be some other column closure, S of B, that equals A. For example, if B is the greatest element less than the greatest integer less than A over 2, then A is either 2B, right? A is either 2B, so it's definable from B, or if A was odd, this A will be 2B plus 1. But it's definable from B. Doesn't matter the exact definition, it's definable. So for selective type, anything that's definable from A is either going to be in the column closure of 0, or if it's not, you could go back and define A from that element. Okay, so that's a selective type. By the way, those who know minimal types are selective and more. They realize even more than that. But and a lot of it is in the book of Kozak and Shmerel. A lot of discussion. You can read about that. I think it's in chapter 3 of that book. Unbalanced selective types are actually rare. And in a very important paper of Kozak, Kotlarski, and Shmerel from 1993, they proved that there are labeled gaps which realize selective types, and then they proved also that there are labeled gaps which do not realize any selective types. So now we can split the case of selective types into two, of labeled gaps into two, selective and not selective. And then they introduce a similar notion. Every selective type is actually quasi-selective, but there are quasi-selective types which are not selective. A type is quasi-selective if whenever A is in M satisfies P, then the column closure of A only defines element in the gap of A, or its column closure of 0. So it only defines element. And it's very similar. You can prove that every selective is quasi-selective, but not vice versa. Actually, yeah, every selective type is quasi-selective, but actually there are quasi-selective types which are not selective, and in particular, they're not rare. Same paper. And finally, they prove that there are non-labeled gaps realizing selective types, and non-labeled gap, I should have said quasi-selective types. Now, non-labeled gaps realizing quasi-selective types. and non-labeled gaps with no elements realizing quasi-selective types. So that gives us 4 cases. The first 2 are for labeled gaps. One is rare and selective, the other one rare non-selective. And then the other 2 are for non-rare, non-labeled gaps, not rare and quasi-selective, and not rare and not quasi-selective. So what happens for each one of these cases? Well, each one of these cases, and I don't have much time to show, but in cases 1 and 3, all the invariant cuts happen here and up to M0. There's no invariant cuts in between M bracket A and M0. And it's really almost complete. You can prove that using the fact that A is quasi-selective. Because if you have an element here and a cut here, you can show that there's another element, if there's a C here and a D here, such that the type of C with A is the same as the type of D with A. Otherwise, you could have defined one of them from A, and we can't because it's quasi-selective. And therefore, there is an automorphism fixing A that moves C to D, and which means that I is not invariant. Next, if you have case 2, type is rare and not selective, you can show that because it's not selective, there will be invariant cuts by the fact that not selective means that there's other things you can define, not only here and there, but other stuff you can define from A, so you end up with invariant initial segments everywhere. And finally, that's the hardest one. This is not always certain for 4, but again, in the same paper, they gave an example where you have a type like which is not rare and not quasi-selective, but has, again, infinitely many invariant cuts in between them. Even though there's not, A can move to a B here because it's not rare anymore, but for some reason, those automorphisms still fix some element here, D. I guess it implies that, yeah, so if D moves, the whole gap has to move. It's almost like the moving gaps lemma, but not exactly. And they show that. So here is the picture, final slides. And I have a minute or 2. Yeah. So here's the first picture, rare and selective in models other than true arithmetic will look like this. These will be the invariant initial segments. Rare and not selective, this will be the picture. Not rare and quasi-selective, the invariant cuts will be here, plus M bracket A. All of them will have M bracket A as invariant, by the way. And in some cases of not rare and not quasi-selective, this will be the picture. Maybe it's a good project to see if we can prove it for all cases or show that some cases actually are the same as this, even though it's not quasi-selective. But that we don't know. But these are the 4 pictures. So we have different invariant initial segments. In the case of true arithmetic, remember n equals to m0. So n is the first invariant initial segment close under exponentiation. And then this is the picture of rare and selective, rare and not selective, not rare and quasi-selective. Not in some cases, and this is some cases of not rare and not quasi-selective. Now, I'm hesitant to label them in terms of closed normal subgroups. That's not always going to be the case, that since these are different, the closed normal subgroups are different. So we have to be a little careful because we don't know if we adjoin 2 orders of a counter set. What happens in this case? Is it the same as just one counter set? Can we look at the difference? The order type of these invariant initial segments is the counter set, but then what happens if we have 2 of them? So we have to look at this. This is definitely different. This definitely is solved. There's only 3 closed normal subgroups, and actually 1 invariant. Just M bracket A is the only invariant. So that's the case here. But in other cases, some cases we were able to show, some cases we were not. But definitely the invariant cuts are different. What's not known for sure is if that implies that the closed normal subgroups are different, or the automorphism groups are different. Okay, so that's all I have. So thank you. I know I have like no time, but any questions? Quick questions?
I think we have time for questions. So let's thank Erez. Looking for my reaction button. There we go. And we can take questions. I see Roman has joined, so.
Oh,
And I have a question.
hi, Roman. Yes.
No, sorry
Still sharing,
but
right? Yeah.
I will listen to the rest of the lecture that I missed online. But what was the main result that you talked about?
Okay, good. So first, the first 40 minutes, I just outlined other results and what Ermek talked about last time, showing to look at. So the main thing was to look at non-isomorphic automorphism groups to show that they're non-isomorphic automorphism groups. So already it was known that just short recursively saturated have different automorphism groups as topological groups than short arithmetically saturated. So that was already known based on your result with K and Kotlarski using maximal subgroups. So that was the first result, and then I mentioned the result that you had with Schmerl, that if the standard systems are different, then the automorphism groups of arithmetically saturated models are different. And then I showed really copied, asked Ermek to use his slide. I copied this result from Ermek's talk from last meeting, showing that in some cases, not as determined as here, in some cases, if the standard systems are different, the automorphisms will be different, but we need this condition to on and then also from Ermek's talk, showing that sometimes if the theories are different, so if this doesn't is a theory of RT2, for example, and R2n, and this is not, then their automorphism groups will not be topologically isomorphic. So that's also a new result, but Ermek discussed it last talk. And then the main result I was showing here was improving the result I had from my dissertation. So if you recall from my dissertation, I showed that if the gap of A realizes rare types, if it's a labeled gaps, it will have different automorphism. It will have the automorphism group of these models will be different than that by looking at the closed normal subgroups. They have different closed normal subgroups. This has a chain that keeps going, and this one has a last one or first one, depending where last in terms of invariant, first in terms of closed normal. So my result that I was talking about only in the last 10 minutes was about showing that we can look at different labeled gaps and different non-labeled gaps and show that there are additional invariant
that part I already listened to.
Right.
All right.
So then I looked at selective types versus
right.
Yeah, so rare and selective versus rare and non-selective, not rare and quasi-selective, not rare and not quasi-selective, and really came with these possibilities. But it doesn't always imply that the closed normal subgroups are different, because if you adjoin two Cantor sets, you can think of it as one Cantor set. So I don't know if we can still recognize it from the model. So this is the next big project. So if I have, two trees like this and I order them in the natural way, if I put them together, I can think of it like this, and that's another binary tree. So, so is this the same as that? I don't know. So the question is, if I can determine this, if I can have a property that's unique to this gap or to this initial segment based on the automorphism group, if I can do something like that, if I can recognize this, and if I can recognize M of 0, then definitely I can distinguish those cases, and that would be, will solve a lot of this, a lot of these questions. Here I don't have much, so even if I look at this, the only one that I can completely determine is this, the non-rare and quasi-selective, because that has only one non-trivial closed normal subgroup, M bracket A. That's for models of true arithmetic. There were other cases that we were able to distinguish, but not too many. Yeah.
All right. All right. Thank you.
Yes.
Thank you.
Yes.
Yes, I have a question.
Yes.
That slide. Are you saying that every countable short recursively saturated model falls into one of these four classes, and that we have examples of the existence of each of these four types?
Yeah, let me go back. So yes, so let's go back to this one. Doesn't matter which one I'm looking at, but if a type realizes if the last gap has an element realizing selective type and it's unbounded, so it has to be rare also, then the picture will be this way. If it realizes rare and not selective, this will be the picture because it will define some elements here. Can we refine it more? Yeah, I think so, but I don't know by how much. And I don't know if we can just, that's just looking at the invariant initial segments. There are other things that we can look at, other types, maybe minimal types and selective types will be different. The rare and selective is also the minimal. That's the same case. But maybe there's some other fact that can distinguish between a last gap that realizes selective type versus a last gap that realizes a minimal type. So selective not minimal versus just minimal or minimal type. So is this so I think we can refine it more, but for this case, this is the picture. But so I don't think there's much more we can do, but we can look maybe if something happens here, if something is different here between those. Or between M0 and the invariant initial segments. So maybe then we can refine it more around here. But in general, rare and selective will have invariant initial segments here and there and nothing here. Rare and not selective will have invariant initial segments here and here and here. But again, exactly how it looks, maybe there's other differences. We can refine it better. But it is improvement to just looking at this. Before we just looked at this picture, so labeled versus non-labeled, and now we're looking at how is it labeled? Is it labeled with a selective type or a non-selective type? And if it's labeled with a selective type, that's the invariant initial segments. If it's not rare and not selective, this will be the picture. What about non-labeled? If it's if it's a quasi-selective, it will define no elements here. We can jump over every initial segment. So there's no invariant initial segments here, but there is a M of bracket A, which will be the last one. Here also it will be the last one, but the question is, does this keep going all the way up to M bracket A, or is there a gap here? And would that make a difference? So again, this is just a first refinement. It could be refined more, but in terms of rare and selective, that's always the picture. Rare and not selective, that's the picture. Not rare and quasi-selective, that's the picture. The only thing that I didn't have is for this one, not rare and not quasi-selective. I don't know if that's always the picture. There are some cases where this is the picture, but I don't know if it's always the picture. The argument what was used in the paper was like similar to the moving gaps argument, but it didn't use the fact that it's not quasi-selective. It actually built a specific type. So I don't know if that's always the case for this case, for the last case.
Oh, and maybe sorry. Laurie, did you want to say? Yeah.
It's that's a separate question. I think maybe I knew this once and I've forgotten, but on the face of it, you could have a hierarchy of types of saturation between recursive and arithmetic by taking delta n saturation. Does that make sense?
I think so. I think that's something that is in Roman and Jim Schmerl's book, where they mention that they can construct, like they start with a Scott set and then close it, like add some elements and then close it under like some delta 2. I'm not sure exactly that construction, but
I
they
think
create.
I don't think there's actually a hierarchy. Maybe I'm wrong about this, but I think as soon as you have sigma 1,
then you have everything, yeah.
then you might end up getting everything. So I'm actually thinking about comprehension, but if you're thinking about a Scott set that's sigma that has sigma 1 CA, then you end up getting ACA.
Right, but I know there was a construction that was created where you started with a Scott set and then you create another Scott set whose models are just recursively saturated. Even if you started with arithmetically saturated, you made it bigger. But actually, when you look at the model that has this standard system, it is just recursively saturated. And then again, you can close it under arithmetic comprehension. It will be arithmetically saturated, and then again, add more elements and make it. So I don't know how these models are like related in terms of like, do we have a copy of one inside the other or not? It would be interesting to know, but yeah, I don't know if that's. I don't know if that answers the question. Your question.
Yeah, thank you.
Right.
But so now one more question that one could ask, because then what Erez is mentioning, those are results for full PA, well, for full, in a sense, for full recursive saturation, and it's really important that you have sequences of elements from different gaps coding the standard system. So it's still open whether you can do anything like that for short models. Where and Ermac hinted at some variants of it, but it's only you get results for topological groups only, because then in the case of model, of recursively saturated models or arithmetically saturated models, actually, you have the small index property that's used to eliminate topology. So that's sort of like this additional big step. Actually, it's not a small step that helps to do this, but it's a crucial step. So we don't know anything about the small index property for these short models. Well, I suspect that they should have it, but the additional question is, do we know anything about differences in automorphism groups of just M0 when it's non-standard?
So I didn't really look into that of the extremely short case. I think there were some results about extremely short, but
there was a series of papers by Kotlarski and some of his collaborators, analyzing, in very minute detail, all kinds of the structure of what's really happening there, various kind of special cuts in between the definable elements, and there were some connections to the properties of the automorphism group. But there were results about automorphisms, but not really about the group, as far as I remember. We were taking another look at that.
Yeah.
Any other questions? Or?
I also have a question about, well, it's about Ermac's results, or maybe I should have asked him, but the one about with Ramsey's theorem for n-tuples. And in a lot of contexts, once you have Ramsey's theorem for triples, you have it for every n. But the statement of that theorem seemed to imply that wasn't true here. Is that the case?
So I wouldn't be able to answer this question. I wish Ermac was still here, but let me see.
Right.
Right. So yeah, right. He said for every n less than omega, this if and only if that. But so It could be
If you
that
take
this is
this,
only finite number of possibilities, maybe. I'm not sure because I know he had a similar result where he had only finite number of possibilities for short arithmetically saturated, but then he extended that. So I'm not sure.
if you had the standard systems instead of the representable sets in a theory, then that collapses at n equals 3. But the way that's stated, it looks like it doesn't collapse.
Maybe. Yeah, good question. I'm going to ask him that.
Well, I asked something similar last week, and because the proof that Erez outlined or talked a little bit about uses sequences of elements that are two indiscernible, and he just used like RT22 to get those two indiscernibles. So perhaps there is some equivalence there with higher exponents, but I don't quite remember now what his answer was. His answer was actually yes, something like yes, something can be done. We would have to go to the recording.
Yes.
Okay. So let's thank Erez again. Thank you so much.
Thank you, Erez.
Thank you.
We're looking forward to when the draft of your paper will come out. So hopefully let us know. And Roman, I think would you like to preview what's coming up next week?
Right. So next week is something specifically for Laurie, but also for the rest of us. This is Dan Isaacson from Oxford. He's a philosopher of mathematics, but especially this area of arithmetic and independence results. But he will not talk exactly about the sort of independent results that, there is something that's called Isaacson's thesis that's somewhat controversial, and Laurie knows everything about it. But he will talk. Will actually.
No.
He will talk about some work of Dennett about the notion of natural number. So it will be somewhat philosophical, but probably good for all of us. And so if you have any philosophically inclined friends, feel free to invite them. I will invite some.
Okay, so please join us for that next week, and keep your eyes posted for the rest of the semester. We have this next week, and then we have the Jim Schmerl birthday conference in a couple weeks after that. So keep your eyes peeled on your email for that, and thank you.